Alright, in this example, what we're being asked to do is a fairly extensive and difficult analysis that in short order you'll be impressed about your ability to do. And that is that we've been asked to find the equations for the slope and the transverse deflection of this beam. So for instance, with this load and those simple supports at the end, it might not be surprising to see that the whole beam would sag in a smiley face kind of way, and so we're being asked to find that transverse deflection, that's this right here, and the slope of that, which of course is the first derivative of the transverse deflection along the length of the beam. Alright, that's what we've been asked to do. Now we've been told it's a steel W18 by 55 beam, so eventually we might want some properties. We don't usually typically memorize these, so we have to go look them up. There's your 18 by 55, and we would, without any other information being provided to me as the structural engineer, I would probably assume that we have bending about the strong axis, which would be a second moment of area of 890 inches to the fourth. And being steel, then of course our modulus of elasticity would be usually taken as 29,000 KSI. Right, now the critical governing equation that we're working with here is that the second derivative of the moment curvature relationship, which will be EI times the second derivative of V, is going to be equal to the load intensity. Right, and the load intensity is this distributed load that we have, which is triangular and acting downwards. Alright, so we need to identify the coordinate system and our boundary conditions as our first step in order to begin to solve this fourth order differential equation. Right, so typically we would put our coordinate system here at the lower left. There's your x, and that would establish that upwards would be positive for our transverse deflection. So there's your coordinate system. So x equal to 0 at the left, x equal to 18 feet over here to the right, and so our L is 18 feet. Now note, I'm going to probably use symbols here throughout much of the work because this is going to be a lot of calculus, and it's easier to work with the symbols than all the numbers that are going to end up showing up here. Right? So let's look at what we've got. Identify the coordinate system and the boundary conditions. I come over here at x equal to 0. And I know, oh, it's a simply support beam here. So that tells me that by definition the moment must be 0 at x equal to 0. Likewise, because of the roller support that we have over here, at x equal to L, or 18 feet, our moment would also be equal to 0. Yes, I could solve for the shear at either end, but that's not a boundary condition. Boundary condition specifies that we have no transverse displacement at x equal to 0. That's interesting. So at x equal to 0, V is equal to 0. And I'm not going to specify anything about the rotation. It'll be non-zero because I'm going to allow the moment to be free right there. And at x equal to L, then transverse displacement is also equal to 0. So I have no shear boundary conditions here. I only have two moments, and I have no rotational boundary conditions. I only have the transverse displacement at both x equal to 0 and x equal to L being 0. Right? Next part, before we can really start to do anything here, is to go find out what our load is. Right now, the problem statement says the peak intensity of this snowdrift load is 300 pounds per foot out here. But notice that's a gravity load, and that's acting downwards. So at x equal to 18 feet, or x equal to L, Q is equal to a minus 300 pounds per foot. Okay, that's interesting. And, you know, checking out the units and all that kind of stuff. Interesting. Well, at x equal to 0, Q is equal to 0, and we have a linear variation. Oh, well, that means that we have a y equals mx plus b, where the b-intercept is 0, and all I'm going to be left with is this slope value that is going to be, that's interesting. Well, I know that it has to end up at minus 300, and that rise happens over the 18 feet, so that'd be pounds per foot times x would be our function. Just check it out. At x equal to 18, 18 feet over 18 feet cancels out, and I'd have a minus 300 pounds per foot, just like I'm supposed to have. Right, now this is going to get really tedious to write this out in this fashion the whole time. So I'm going to call this a Q naught, and yeah, I'm just going to call it Q naught time, what do I want to do? Do I want to mess around with over L? Yeah, I guess so. Q naught times x over L. It's going to be a little bit of annoying, but Q naught here then is going to be equal to minus 300 pounds per foot. Is what that's going to amount to. So being in symbols, that'll be a little bit easier to work with. Right? Again, check it out. Put in x equal to L. L over L goes away. I'm left with Q naught for the intensity of the load, and that's minus 300 pounds per foot, just like it's supposed to. Everything else is a linear variation in between. All right, now we find the shear function by integrating the load function. Right? The shear is equal to the integral of the load. We just found out what that loading function was. And then we evaluate that. That's Q naught x squared over 2L. And that's where people will make the first mistake. People, it's an integration. There is a constant. And there's going to be a bunch of them. So call it C1. You've got to have this. If you don't, just give it up right now. Don't even bother wasting your time. Go do something else. You've got to have this. This is why you took calculus, is so that you would learn all of these little pieces right here. The whole reason for your calculus torture is this right here. We got to have that constant of integration. And what's even more, in this case, look at our boundary conditions. Not a single one of them, of the two, involves the shear. So no boundary conditions with shear. So move on. We can't evaluate this thing. We can't do anything with it. Right? We have to go to the moment function. Right? And the moment is the integral of the shear, which we just found out is this expression here. Integrate that, we get then Q naught x cubed over 6L plus C1x. See, that was the big key. If we didn't have this, we wouldn't have had it down here, and we've been all wrong. Plus, well, we got another one that popped out here, another constant of integration. But note, we've got two boundary conditions associated with the moment, and so now we can go figure out what these are. M at 0 is going to be, alright, that would be Q naught times 0 cubed over 6L plus C1 times 0 plus C2. We'll set that equal to 0, and therefore, why did I set it equal to 0? Because the boundary condition at x equal to 0, m was equal to 0. Not just some generic, oh, it's equilibrium, I guess you're supposed to set it equal to 0. No! It's whatever the boundary condition says it must be. And we find out here that C2 is equal to 0. Likewise, now we go evaluate the moment at L, because that's where the other boundary condition is, and we get Q naught times L cubed over 6L plus C1 times L. And here again, because the boundary condition is, the value of the moment is 0 here, we set that all equal to 0, and we then find out that C1, which so many people want to drop off, they don't want to include it, but it's not 0, doggone it. It's non-zero, and indeed it's a negative value here, negative, and Q naught L over 6. Right, leaving us then a moment expression that is Q naught x cubed over 6L minus Q naught L times x over 6. Now note here something. Let's check units. We've got a Q naught in both of them. Okay. I've got a length cubed over a length, so that's length squared. Alright, well that'd be force over length times length squared, giving me force times length, which is what a moment is. Good, check. Likewise, Q naught times L is just going to be a force. X is going to be of L, so force times length. Again, I've got units of moment. That's all got to work out. If not, it tells you that there's something wrong, and you need to check those units now. There's just too much work here to mess something up and find out 15 minutes later that, oops, we made a silly mistake, like we didn't include the constant of integration because we didn't think it was important to include. Actually, it usually gets dropped off because someone has a little calculator, not this one, but someone has a calculator that can do integration, and that usually that calculator does not show you that constant. You've got to be an intelligent user of the tool that you've decided to use. Why am I being so sort of dogmatic about this? Because this is one of the key mistakes that I see made over and over and over, and oh, by the way, over and over and over. Alright, curvature by the is our next step, and curvature is equal to m over ei. Right, so we take whatever we found for the moment function and we divide by ei, and so that here would be this expression. Now usually e and I are not functions of x for most of the problems that we're working with, and so a lot of times people will find it more convenient to take the ei over here and just work with it in that form. Right, now we have curvature, and well, this is really just calculus from here on out, right? Because now we've got that if we want to find the slope, well, the slope is the integral of curvature, and again I'm going to multiply by ei in both cases, so ei theta would be the integral of ei kappa dx. When it's a constant, it doesn't change anything that we've got in here, so that's okay to do that in that instance, and it does just make all this work a little bit easier to process. If ei is not, then we got to deal with how it varies. Right? Yeah, this gets pretty long, doesn't it? Right? And yes, you have to do all this. I hear this all the time. Do I really have to? Yes. Well, but that's calculus. Yes. That's why you took calculus. Well, okay. Yes, good. And don't forget the constant of integration. And, of course, we have no slope boundary conditions, so I can't do anything about evaluating C3 right now. Alright, well, what do? Well, we come along and we do our last integration, right? This is the fourth step in this whole process. And so, integrate here, q naught x to the fourth over 24L minus q naught Lx squared over 12 plus the C3 dx. And now we get q naught x to the fifth over 120 L minus q naught Lx cubed over 36 plus C3x plus C4. Wow, 4 integrations. And note here, we're trying to get to a displacement, so L to the fifth over L would be length to the fourth, integrated 4 times. We should get something like that, L to the fourth kind of business showing up here. Same thing here, L times L cubed, right? And the fact that we only have C3x tells me something that probably C3 is going to be something like an L cubed. And I don't know what C4 is, but oh, that goes back to our displacement boundary conditions that we had back here, that we knew where the displacement was 0 at 2 locations. So let's go find those, right? That we know the displacement at 0, so that would be ei times then all this stuff, which really should have been ei, right? All that stuff. All right, wait a minute here. This would be q naught 0 to the 5th over 120L minus Q naught L 0 cubed over 36. Why did you write it out if it's just 0? To show you that it's 0. Plus then C4, set that equal to the boundary condition, which was 0 right there, and we find out that C4 is 0. Right? One more to do, and that's going to be the displacement at L, right? And so, and by the way, I multiplied this whole expression by EI, so this really was multiplied by EI also, but it was 0, so it went away. Right? And then here we get Q naught L to the 5th over 120L minus Q naught L cubed over 36 plus C3L, and that's going to be set equal to the boundary condition here, which is 0 times EI, or 0. Right? And so now when you go through all of this business, notice we get Q naught L to the 4th as a net that gets factored out there. Right? And then it gets divided by L. So we have that there's going to be some sort of constant that's sitting here to all work out, and that all that working out is going to be, let's see here, how is this going to work? Might have to do some little work myself here. Q naught L to the 4th, 1 over 120 minus 1 over 36 is equal to, take that to the other side, minus C3 times L. Alright, so now let's put this back over here. That's a plus, plus, minus. And let's see, we can factor out a 12 out of this. So that's 1 over 12 minus 1/10 plus 1/3. I'm sure I might be too low on the page there. Alright, and there's still a Q naught L cubed sitting there. Right, that equals the C3. Take that to minus 3 plus 7 all over 30. Oops, plus 10. Got ahead of myself there. And that's a 1 over 12. So that's going to be a net that C3 is a positive 7 over 360 Q naught L cubed. And that leaves us then finally an expression for our displacement here that is V equals 1 over EI times Q naught x to the 5th over 120L minus Q naught L x cubed over 36, and then plus 7 over 360 Q naught L cubed. And again, note the units that we've got here. We have a Q naught L cubed here. Ooh, I don't like this. What did I leave off? I left off an x. See, that's why I wanted to check our units. Q naught L to the 4th here. Q naught L to the 4th. Q naught L to the 5th over L is Q naught L to the 4th. That's pretty important here. That's also force over length times L to the 4th. So that's force times length cubed over force length squared. So that's going to give us L as our units on V. Wow, I liked all that. Now, of course, this is not an uncommon problem that's been worked out before, so let's go take a look at maybe some tables that might have this. Your textbook is one that does have this situation, right? In its appendix, it's got all these beam tables, the slope, the deflection equation, the elastic curve. These are usually giving you some maxes or some critical locations, and here's our situation. Right, here's the, ooh, yeah, good. Now note, their W naught looks like it's downwards. That could be important, because when we look at the expression over here, you know, there's a couple of critical things to take a look at. You've got 7L to the 4th here, you got this 3x to the 4th over here, you've got, oh, this is a W, or a Q, times X times L to the fourth over L for the first term, 7 over 360. All right, well, I like that. 7 over 360, that's what we found. And L to the fourth over L is L cubed, so we found that. But there's a minus sign that's been factored out here. We didn't get that. We got a positive. Right? But we do have the same sign on the X term over here as we do X to the fourth term as we do to this one. Oh, that's X to the fifth. Yeah, see, that's the thing, you got to be really careful when you look at all these things. And so it can be hard to peel this apart. Have you done it right? Right, so you got to factor it all back, or not factor it, but multiply it all back out to make the comparison, and check signs. Well, the signs on those two terms are the same, and that's what we had. And then with the opposite sign in the middle, we had 1 over 120. They have 3 over 360, so that's what's going on with that. They have 10 over 360, while we had 1 over 36 here. And the big thing is they got this minus sign because they're going to define W naught as positive acting downwards. We define Q naught as positive acting upwards. You just got to keep track of all that as you do all these this kind of work. Is being very careful about how you set up your sign convention and then working through it consistently all the way. Right? So we end up then finally with that as our version of our equation for the deflection equation. Whew, that's a lot of work, right? 20 minutes of work, and that's why you got to be careful not to make mistakes at little small steps along the way.